So a new batch of material, right? The gaseous state. I don't know. I'm just imagine being Michelin or anything that their livelihood depends on making a product with gas pressure. I mean, tires, all that stuff. You have to be able to understand and predict and control. Control is kind of an odd word. It's more like predicting, and you're kind of, in that essence, controlling it if you're predicting really well, right? Because you really can't control nature. But if you're really good at predicting it, it appears like you're controlling it, right? So if you can control the pressure in your, whatever, the tire or whatever product you're making, I mean, if this was soda, right, it's going to develop pressure in there. And how do you know how much pressure that is and what it can... So if you can have an idea what pressure is going to be in there, you can make the product to be, you know, it doesn't have to be super strong. It just has to be able to withhold what's there. Otherwise, that little bottle of soda is going to be that much more expensive. They build, or the tire, or whatever. So being able to really predict things well will really help things out. So that's kind of what we're heading at, and being able to understand. So if we think about pressure, some common units for pressure. Gloriana, what have you heard of as units for pressure? Has anyone heard of, what am I getting at? Some units for pressure that you've heard of. On the tire it says one. PSI. Now what's PSI? Pounds per square inch. So there's one of them, PSI. Pounds per square inch. But we're not going to use that one. Anybody know any more? Pascal is another one. They call it capital P small a. That's Pascal. That, I don't know, man. If you're in Britain, see, I don't get out much. I've never been across the ocean. I don't know if anyone who has. But I'd be interested to know what units they use for pressure. Right? You know, when you listen to in Britain, but if you listen to the weather here, they don't say PSI. Oh, it's so many PSI pressure outside. No. That for temperature. Atmospheres, ATM, there's another unit of pressure. ATM, atmospheres. And the pressure on Earth is exactly 1 atmosphere if you're at what? Sea level. If you're at sea level, then atmospheric pressure is exactly 1 atmosphere. The one that I think we're going to use the most hasn't been mentioned yet. Kelvin's temperature. We're going to be using that one, though, Yesenia. Little mm was, not M&M, millimeters of mercury. There's another one, millimeters of mercury. Okay. Now, I don't know. This can't be before your time. That Terminator movie, not the #1, but I think it was #2 when the guy who came after him, they blast him with a shotgun, all that silver stuff came flying off, it hits the road and it all rolls back up again. Remember seeing that stuff? They just use mercury metal, right? And it's a liquid, but it's really, really heavy. Okay? And we'll talk about it a little bit more, but millimeters of mercury and where that's coming from. Okay? Now, I guess I'll talk about it now. So here's a little barrette, right? And if I open the stopcock at the bottom, the stuff will what, Desiree? It'll come out, yeah, right? So I don't know if you can see that. It comes out. Now, right, did you see that? All right, I open it, stuff comes out. Fine, we expect that. What if I, Janet, put my thumb really nice and tight on the top, right? And now I open it. come out. Well, I can get it tight enough. There it goes. Right? Why? Circulating's a good idea. Now, think of pressure. I'm really pushing down hard on here. Something has to be pushing in which direction? Has to be. Otherwise, this stuff is going to fall out, right? So what is pushing back up? Atmospheric pressure. What is... Atmosphere is mostly nitrogen gas, yeah. But what is atmospheric pressure? Right? All this stuff, right? Air. Does air have mass? Is it made up of little molecules? Yeah, so they all have mass. And it's thick. It's thick. So if you take a column, like 1 square inch, exactly 1 square inch, and go all the way up to the outer reaches of, of our atmosphere, how much weight would that be? Take 1 square inch. Oh, that's not really a square, but 1 square inch, tabletop, go all the way up, 14.7 pounds if you're at sea level. What the weight of a nice-sized baby, right? That's pretty heavy. So that's what's pushing up. We're used to it, though. In fact, we have that pressure inside of us and outside, so it's really no big deal. But so that's what's pushing up on it. My thumb's blocking it, so it's not pushing down on it. Right? Because now that height only goes up to here now. The rest is blocked. So that's what's pushing up on it. Now, this is what's curious, is they could use this. This is just water. I've added some blue food dye. You hear on the news, oh, we have a cold front moving in. The pressure's dropping, right? They have to be using something to measure the pressure. They could use this. What they would need to do is just have more water. Because at some point, right, this is going to start dripping out of there, won't it? Because the weight of the water is going to be the same as the pressure pushing up on it. At some point, it's going to start dripping out. Can you imagine that? Just need to have this height be, in fact, it needs to be about 3 meters high. It's going to have to go through the ceiling. It's going to be a really tall column of liquid water. Really tall column of liquid water, and the stuff would start dripping out. And then it would start dripping out at different heights of liquid water, depending on what the pressure, the cold front moving in. Make sense? Okay. But to say you have, oh my goodness, like 700, 900 inches of water is the pressure, this doesn't make sense. Instead, they're going to use mmHg, millimeters of mercury. They're not going to have water in the tube. They're just going to have mercury in there. It's a lot heavier, so you don't need it to be so darn high. That's why. They can use anything. But as long as everyone sticks to mercury, everyone will know what everyone else is talking about. It's easy to make. It's not so high. In fact, one atmosphere is how many millimeters of mercury? We don't need to know all these conversion factors, but does anybody know? That thing needs to be 760 millimeters high. Then it'll start dripping out, which is 760 millimeters, about 76 centimeters. It's not that high at all. And the mercury will start dripping out. Okay. Oh, I forgot about something. Okay. So I said that we have how many pounds per square inch, Jessica, of atmospheric pressure? What was the number I said? 14.7, around 15, right? So and I did this, I measured all the square inches on this can, all sides. And so I measured the square inches, multiplied it by 14.7 pounds per square inch, and I got about 330 pounds or so. So 330 pounds, but a real nice size football player, fullback, whatever. That's how much pressure's on this can. I mean, if that guy steps on this thing, it's going to, right? It should completely crush. Well, why doesn't it? Science says there's 330 pounds of pressure on this thing. I don't see it getting crushed. Is this something we make up just to solve problems? Because this thing, because the shape, he would step on it, it'd crush. What's inside of it? Not nothing. If nothing was inside, definitely we get crushed. But there's air inside. So you have 15 pounds per square inch pressure on the outside, but you have what pressure on the inside? 15 pounds per square inch. It's kind of like the circulating idea Christina was talking about. It's the same everywhere, same inside. So if I can remove all the air inside this can, it should then what? It should crush from all directions, right? So that's what I'm going to do. I'm going to remove all the air inside this can. And I'm going to do this. Maybe Bill Nye, the science guy, is still around, isn't he? Or not? He died? Oh, I did not know that. That's so sad. Anyway, I stole this from Bill Nye, the science guy. And what you do, if you're really bored someday, you just want to crush all your cans. Okay, you saw me. I dumped some water in there. Okay, so now what I'm going to do is I'm going to heat this thing up, get it boiling. And once it's boiling, you're going to see what coming out of here? Water vapor, steam. It's just water, right? But in the what phase? Gas phase, right? It's still water. But okay, so the point is I'm going to, in the can, is it going to crush at that point? No, right? It's just steam boiling out of there. So, but it's not crushing, so that means there must be what pressure of steam inside this can? An ATM, 15 pounds per square inch. But it's steam now. It's not air. So if you're inside there, you'd be dead. There's no oxygen. All it is water vapor. Right? And plus it'd be really hot. But the point is that I'm replacing all the air with steam. What happens with steam when you put it on something really cold? Condenses is the word, right? Turns from a gas into a liquid. And does the liquid take up a lot of space? All right. Now this is where you pretty much have to be playing around with this. If you're boiling water on the stove, right? You put your hand over it or whatever to feel the steam. Don't you just get little tiny water droplets on your hair and on your arm, right? So gas takes up a heck of a lot more space than a liquid does. So when I put this can of steam into this, that steam is going to condense into a really thin film. Because aluminum conducts heat really, really well and really fast. So this can's going to get really cold really fast, and the steam's going to condense into a really thin layer. There's nothing inside the can. It's now starts with a V, vacuum. It's now a vacuum. There's nothing in there. Well, there's nothing in there. Now there's nothing pushing back. Okay, now there's another trick to doing this. If I just put it in the water with this up, it's not going to work. Right? Because then it condenses, then air just rushes inside really, really fast because there's nothing in there. So I need to do what to this can before I put it in here? I need to turn it, flip it upside down. So that's what I have to do. See if I can get this lit. There it goes. Okay. I'll get it boiling. What's that? Okay. Now you guys might get a little wet. I don't know. We'll see. It's just water. Now you can see this is cold water. I put ice in there. So right now the can's filled with what? Still air, right? Because there's no steam shooting out. Something's going on in there. It's starting. I can feel it starting to boil. Little bubbles. It's starting to go, right? Okay, let's get it going really good. So I'd say now, is the can crushed? No. So that means the pressure of steam inside must be exactly what? Exactly 1 atm, or whatever the pressure is in this room, right? And we're above sea level, so it's going to be a little less than 1 atm, a little less than 14.7 pounds per square inch, but that's the pressure of the steam in there. So I keep it boiling, flip it upside down as fast as I can. All right. Usually I can get a louder crunch, but I didn't get it deep enough in the water. But, right? All sides. So why aren't you crushed? Right? Why aren't you crushed? I mean, there's a lot more than 300 pounds of weight on you because you have what inside you? Air, right? Same pressure. Okay. So you're balanced. Okay, so we're going to try to predict final pressure, temperature, or volume of a gas. Right? You can't control this stuff, but if you're good at predicting it, make it appear like you're controlling it. What happens to gas pressure when temperature is lowered? Victoria, what do you think? What happens to gas pressure? The millimeters of mercury, the psi, the atmospheres, the pascals. The gas pressure goes lower. Why? She's right. Paulina, why? Why would the pressure drop if you make things colder? Oh, kind of, yeah. Now the little molecule doesn't essentially change its size, but they're going to get closer. They start moving faster or slower? Slower. That's all temperature is how fast things are moving around. So they start moving slower. They're going to hit the sides of the balloon, right? So here's balloon filled with, I just blew it up, filled with air, right? I'm going to make it really, really cold. Then the little air molecules inside are going to start moving slower. So that means, are they going to hit the sides very hard or as hard? No. They're just taking up less space, right? And this thing's should get smaller. Now what I'm going to use, have I played with this stuff in here before? Yeah. Liquid nitrogen, right? What is the temperature of it? Here's brownie points. Anyone remember in Fahrenheit? 300 something below zero. Right? 330 degrees below zero in Fahrenheit. Okay. So let's see. Now that balloon should get what? Should break, should what? Should get smaller, right? Hopefully it doesn't break. I mean, that would kind of defeat the whole purpose of this. But how am I going to get it? We'll see. Just try it here. Get down there. There it goes. Okay. Now it should start what, though, as it warms up? It should start getting bigger, right? What? Geez, that's never happened before. Cool. Right?
And then the glass breaks.
Yeah, glass is really tough. Right? So, okay. So Desiree, what law are we going to use to predict final pressure, to predict pressure, temperature, volume? They call it the ideal gas law. What was that? You remember reading it? Anyone remember this equation? PV equals N RT. There it is. That's what we're going to use. Okay. Before we, let's see, before we get into these questions, and we're going to have another equation, but what is all this stuff? Lauren, let's start. Yeah, what is all this stuff? Recognize any of them? Yeah, just assume. P is probably what? Pressure, right? Jacqueline? What's another one? V is volume. Erica? Yeah, T is temperature. See, it's not too bad. Bianca? You're only left with N and R. Anybody know any of the remaining two? No. Because this will work for any gas. So N is the number of, not grams of the gas, but number of moles. Number of moles of the gas. Now all this is a lot easier to remember if you just remember what R is. To me, R is the key to the whole thing. Yeah, it's ratios. It makes all this stuff work. It's a ratios. It's a constant. It's called the gas constant. And I give you equations. I give you the constants. But the point is, if you look at this constant, you pretty much know what everything else is. Let me show you why. If you look up this constant, this is the one that we're going to use, I think, the most. Okay, 0.0821 ATM times L all over moles times K. So Christina, I'm saying that if you know this R number, you know what units to plug in for everything. If we're going to use this R, what units would you plug in for pressure? It has to be what? Specifically, what units? The ATM, right? So if the question gives you in millimeters of mercury or whatever, you're going to have to convert. And I give you conversions. Okay. That volume had better be in, oh, here's a no name, Janet, what units? Volume had better be in, according to this thing, what units of volume do you see up there? Not milliliters, but no volume. Everyone see it? It's got to be liters. Volume has to be in liters. And we already said little n has to be moles, right? Because there it is. Temperature, David, has to be in big K, Kelvin. How do you get things into Kelvin? Convert, yeah, but it's not a multiplying. The temperature in Celsius, the temperature in Kelvin. There's no degrees. The temperature in Kelvin is what plus the temperature in Celsius? Does anybody know? 273. Yeah, just add 273 to it. And all the homework, they always give it to you in Celsius. So you got to convert it to Kelvin. Otherwise, you can't use that equation. Use the right R. Okay. Now, there's the problem. Gloriana, there's the problem. We want to predict final pressure, final temperature, or final volume of a gas. If you look at this equation, Gloriana, how many P's do you see? How many V's do you see? There's only one. There's only one temperature even. There's no change. You see the problem? They're going to say, oh, the pressure is 5 atmospheres, and we made things change to this temperature. What's the new pressure, or what's the new volume? That isn't going to work. Right? We need to mess with it a little bit. Okay. So what we're going to do is we're going to, let's see, bring the nRT over. If I divide both sides by nRT, this is going to equal what? 1. Okay. Now I want to add subscripts. So you can use initials and finals or 1s and 2s for subscripts. Let's add more space over here. Add subscripts. So I have PV over nRT equals 1. So you have, right, P1, initial pressure, initial volume. I just put little subscripts on everything. Now it doesn't make sense to put little subscripts, though, on, I would say, two things, Jessica. What's something that it doesn't make sense to say, oh, I have initial this? It's not ever going to change. Oh, Jessica just took off. Yvette, what's something that doesn't make sense? It's not going to change on you. R. Exactly. R does not make sense to put a subscript on, so we're going to erase that. There's one more, Victoria. And it seems to me it might make sense if you think of this balloon, right? We have initial volume, we have initial pressure, right? We're going to make it a new temperature by dumping this guy on there. The pressure stays the same, still 1 atmosphere on the outside. What would be the new volume, right? We didn't really change what with that? I mean, we could use this. What would be the new volume? We could predict it, but what doesn't change? Now, R doesn't change, Yvette's right, but what else doesn't change? If we were going to predict the new volume of that balloon. Yeah, temperature's definitely changing because, right, we're making it minus 330. Number of moles of the gas. We're never adding or subtracting the number of moles of the gas. So that doesn't change. Right? So what we can do is we can say, do this again, PV over nRT, and just put the finals on there. Right? But remember, it doesn't make sense to have subscripts on N and R, so get rid of them. Right? So we can now cancel what? And have a new equation. What's the same on both sides? N and R. So here's our equation. That I'm going to be P1 V1 all over T1 equals P2 V2 all over T2. There it is. So we have two equations to mess with. We have PV equals nRT, and then we have this one. Yes, Christina?
I don't understand why we don't use subscripts on R and then R.
Oh, R? Because R is the same no matter what the problem is. We're going to look it up. Either I'll give it to you, or you look it up on the inside front cover of the book, or you Google it. R is always the same. R is always that number, 0.0821 atmosphere liters over moles Kelvin. Always. And then we don't put subscripts on N, because no matter what the process is, all right, here's a process. I'm compressing it. What's the new volume? We're never changing the amount of gas in the balloon. So that little N never changes. So that's why we get rid of it. Yeah?
So we don't use the equation PV over nRT equals 1.
Yeah. Because PV over nRT equals 1 is really the same as this one. So I didn't draw a box around it.
Oh, okay.
So
So it doesn't matter. So they're technically the same.
yeah. Okay. Oh, good. Which one do you use? I think you're going to use, if you have what's a question like, what's the new pressure? Or what's the new temperature? Or what's the new volume? You're definitely going to have to use every single time which one? The second one, right? But if they say, what is the pressure? If I give you the volume, the number of moles, and the temperature, then you'll have to use this one. So I think whenever you're trying to predict what a new pressure, volume, or temperature is, it's going to be the second one. And looking at this, look how your units cancel. Because Paulina, when were you, let's jump back up to the first one. If I use this number for R, what does P have to be in? It has to be ATM, right? Everybody, volume has to be in liters. T has to be in Kelvin and in moles. How about the second one? See how you can be a little bit lazy on it? Does it matter what the units of pressure are? Just have to be the same on both sides. So you don't have to have it in ATM, just have it the same on both sides. Volume, same story, but not T. That's the trick to doing this. T always has to be in units of Kelvin. Otherwise, you're not going to get the right answers. T always has to be in Kelvin. Okay? Otherwise, it's just not going to work. Okay. So let's take a look at our first question here. A sample of nitrogen gas at 18 degrees Celsius and 760 millimeters of mercury has a volume of 3.92 milliliters. What is the volume at 0 degrees Celsius and 1 atmosphere? So Desiree, it seems to me we're talking about gases, so we know we're messing with one of these. Which one is it? Oh, nice. Did you see how she deduced this? I don't know if you heard her. She said, is it going to be the second one because you have two temperatures? There, yeah, that works great, right? Or you can see that you have two volumes, right? Because here's a volume 3.92 milliliters. They're asking for a new volume, right? You have two pressures, 760 millimeters of mercury and 1 atm. So there's a lot of hints saying you better use the second one. Okay. So, Lauren, we're going to use the second one. How many variables are there in that second equation? How many things can change on you? 3, but keep counting. There's 6. That means in that question, Jacqueline, they had to give us how many? They had to give you 5. So I guess we should just start listing them out, right? We're not using this one. P1, V1, T1, start listing over here, I guess. P2, V2, and T2. Okay. Maybe let's start, Erica. Which one of these are we looking for? Yeah, volume, but which one? Would you V1 or V2? Yeah, V2. I agree, but really it doesn't matter as long as you're consistent. All right? What I mean is, what is the volume at 0 degrees Celsius and 1 atmosphere? If you want to call that volume V2, great. That means that 0 degrees Celsius has to be T2 and 1 atmosphere has to be P2. But if you want to pick that volume to be V1, fine. But then 0 degrees Celsius has to be T1 and 1 atmosphere has to be P1. See what I'm saying? But usually we think logically, oh, these changes, initial, final, we kind of think of this as final, right, if you're actually going to do this. So I kind of agree. I would say V2. It seems the most logical way to do it. But mathematically, it doesn't matter. Okay, so let's plug in the rest of this stuff, Bianca. What would you put in for, I don't know, any of these? What's that? T1? The 18 degrees Celsius would be T1, yeah. But, you know, since we're listing this out so nice, Christina, I think we should just keep fixing this stuff. Because can we plug 18 degrees Celsius into this equation for T1? Oh, it has to be in what units? Kelvin. So we should add what to it? 273. So let's add 273 to it. Otherwise, we may very well forget to do that. So that's what? 283, 291? So that's 291 Kelvin. And a weird thing with Kelvin is notice they don't put a degree on it. It's just 291 Kelvin. They don't say 291 degrees Kelvin. So it's kind of different than Fahrenheit or Celsius. I don't know why. It's just their convention. Okay, so there's our T1. Another one. Ashlyn.
Pressure is
Which pressure?
The
P1. Okay, and that is
760
millimeters of mercury. Okay. Keep going, Janet. Yeah? Which one, though? Yeah. Everybody agree? Good deal. Okay. David. 2 more.
I have a question though.
Yeah.
Do you have to change the milliliters to liter?
Well, I'm letting you guys decide. If we leave it, it's a good question. If we leave it in milliliters and we plug all this stuff in, it'll be easier to see once we plug in all the numbers and you write in the units. If we leave V1 in milliliters, we do the math, V2 is going to come out in milliliters. So, I mean, we can change it to liters, but, right, why go through the work? Okay, so I would just leave it. Okay, so what's another one?
You know that 0 degrees Celsius would be 13.2.
Good. And then change it to Kelvin. We had 273. Just get 273 Kelvin. All right, that'll be our T2. All right, we need to know a P2, everybody. That's got to be 1 ATM. So, okay, do you see a problem before we start plugging stuff in?
760.
Yeah, they're not the same units, right? So let's pick one. Oh. Oh, 1 ATM is how many millimeters of mercury? 760, so we could just as well write 760 there. All right, but usually you have to convert. It's not that simple. They're going to say 0.5 atmospheres or something, but okay. So now we plug everything in. Okay, P1 is 760. Plug it in with the units because then it kind of verifies that things are canceling out. V1 we said was 3.92 milliliters. All over T1, which is 291 Kelvin. And then we've got P2, which is 760 millimeters of mercury. V2 we're solving for. And where's my T? 273. All right. So I should have wrote that in. But see how the units all work out for you, right? V2 will turn out in whatever units you had for V1. Okay. You remember the trick to doing this? Gloriana, you remember the trick to solving for this stuff? How are you going to solve for V2? Or what would you do?
I would multiply 760 and 3.92 times 273.
Good. And then, yeah, keep going.
And then divided by 291.
Yeah.
And then
So she took 760 times 3.92, divide by 291. The order of this stuff doesn't matter. It's all multiplying, dividing. Then what can you do?
and then
Divide by
760.
760, multiply by 273. Do you remember the game? If you got stuff like A over B equals C over D, right? Right, in this case, we're solving for C, so you have to do that diagonal game, right? Get rid of the D, move it along the diagonal. Has to go up there with the A, right? Leave the A alone. It's most confusing when you solve for D. It's going to happen. You're going to be solving for a T2. How would you solve for D? I'm just to head off an algebra problem here that's coming up.
Multiply C and D divided by A.
Multiply C and B divided by, yeah. Because the D has to go up on top, A goes on the bottom, B goes up there with the C. All right? Make sure you can see that. All right? Move the D up there where the A was. Move the A down where the D was. And now you got to get rid of that B. So move it up there where the C was. So make sure you can play around with this kind of thing because it's coming, right? You don't want that to be your hindrance. Okay, let's see if you get an answer for this then.
So can it be also be written by 760 times 3.92 times 273
Yep.
divided by 293
Yep.
times 760?
Divide by 760.
Divide by 760.
Yep, yep. Because order doesn't matter with multiplying and dividing. All right, it doesn't matter. Let's see. You could also just cancel the 760s, but ah. Okay, I got about 3.68. And my units have to be milliliters. Yeah. Okay. Okay. All right, here's another one. Helium is at 22 degrees Celsius and 1 atmosphere. Occupies a vessel whose volume is 2.54 liters. What volume would this gas occupy if it were cooled to liquid nitrogen temperature, negative 197 degrees Celsius? So, Jessica, it looks like we need to use what equation are we going to be shooting for? The second one, right? Because you can see there's more than one volume, there's more than one temperature, and all this stuff. So definitely we'll be using this one. Oh, hey, before we start plugging stuff in, Victoria, let's just head off some homework questions. They're going to say, it's going to be really verbiage, a lot of verbiage, just like this we just read. But at the end it might say, the temperature remains constant, or the pressure remains constant, or the volume remains constant. What does that do to this equation when they say something's constant? Someone said it. Did you hear them? Say it out loud, or whoever said it. It's going to cancel out. Right? If they say the temperature is constant, that means T1 and T2 are the same number. They cancel out. So whenever they say something's constant, that means just cancel it out in this equation. Because they're not going to give you the numbers. You're going to, well, how can we do it? Right? No, I just cancel them. Okay, but nothing's constant, so we can't cancel anything. All right, so go ahead and start filling this stuff out. Identify what all those variables are. Identify what variable you're trying to solve for. It should work out. If anyone's not sure, just ask. Reading this question, they didn't say it, but which variable actually remains constant? The atmosphere, the pressure, right?
This is with this gas, right? So it's the same.
It's the same gas, but they didn't say anything about pressure, so you have to assume that pressure just stays constant. P1 is 1 atmosphere, so P2 is 1 atmosphere. So you can either put in 1 atmosphere for P2 or just cancel them in the equation. Cancel the P's. You have to assume that from the question. They didn't say it. You just have to assume it. This is similar to the last one we did. Fix that. So did you get around 0.65?
Yes.
Great. All right, let's check out the next one then. And it's liters this time, if you didn't do any converting. Liquid methanol can be produced by reacting carbon dioxide gas with hydrogen gas in the presence of a catalyst. Water vapor is the other product. Okay, now how many volumes of hydrogen require? Okay, now let's talk about that last sentence after you write the reaction. It'll make a lot more sense. Okay. This liquid methanol, Desiree, is being produced, so it should be on which side of the arrow in our reaction? Yeah, the right. And it's a liquid, so I'm going to put a little L on it. And there's another product. Lauren, what's the other product? What's that? Yeah. So I'd write H2O with a little what subscript? G. Okay. And the reactants are, where are they? Carbon dioxide gas. Everybody, that's CO2. And hydrogen gas. Now, I guess the only trick to doing this is that hydrogen, oxygen, nitrogen, all these gases, chlorine, fluorine, they're all what? What do they have little subscripts? A little 2. They're all diatomic gases. I don't know how you're supposed to know that, but they are. They're all diatomic gases. Okay, so we have to balance it. Okay, do H's last, right? I have a C, 2 O's, 2 O's. Hey. 3, 4, 6. Wow, is it balanced? The only thing I have to do is put a what in front of the H2? A 3. Well, I'm good. Oh, that wasn't so bad. Okay, now let's try to answer the question. The trick to doing this is realizing when you have a reaction, these stoichiometric coefficients, we used to think of them as what ratios? Mole. The mole bridge, mole ratios, right? Well, with the ideal gas law, you can think of them as volume ratios too. So instead of saying how many volumes, you could just as well be saying how many moles, but they want to use volumes because we're talking about ideal gas law. So how many volumes of hydrogen gas are required for each volume of carbon dioxide? You would say 3. So it's not that complicated. All right? Hardest part was just writing the reaction. Okay, so that's it. So we have lab tomorrow. If you haven't made it yet, make sure you hit lab. Have a good rest of your day.